we switch gears again, moving to another quantum field of application, namely quantum computing, with Dr. Sofia Valle Corsa, physicist as well. I'm the only engineer in the room, probably. Sofia is a recognized expert in computing and simulation for physics. And today, she leads the quantum technology initiative quantum computing activities. And on Sunday in spare time, she's also an expert of artificial intelligence and application of machine learning and deep learning to physics. Thank you, Sofia.
Thanks. How do I put this in? Okay, there. And this works. Okay. So thanks. I will try to be short, and we get some time for questions. So, but also please interrupt me if you have questions while I'm explaining things. I really like to have this as interactive as possible. So I will show you what we do for quantum computing. I will give you a glimpse of what we do for quantum computing at CERN. And start with a little bit of an introduction. I'll explain to you why, what are the stakes, what do we want to do. So maybe you remember a few years ago, there was already this big announcement that was put out by Google that was claiming quantum supremacy. This was in 2019, I believe, yes. And it started really a discussion about what it actually means, quantum supremacy. Is it really true? Actually, just a few months later, there were other so actually what Google showed was that they could solve a problem in just a few seconds compared to the time that it would take to a big supercomputer like the Summit cluster that is available today, that would take about 10,000 years to solve. Now, just a few weeks later, there were a lot of papers that were published claiming that this was actually not true, that there were problems in the estimates that were made concerning the time it would take to solve the problem classically. One of those papers was published by IBM, for example. The year after, there were more announcements made, this time by a team from the Hefei National Lab in China. They were focusing on a completely different problem, but they also, and they used a completely different hardware technology. But they were also sending basically around the same message. We found a problem that cannot be solved on a classical computer in any reasonable amount of time. Now, if you look at what is actually common between these two claims is the fact that those are actually problems that are not so relevant in practical life. So I wanted really to stress here that I think one of the things that is important when we talk about quantum computing and quantum advantage is that we keep in mind what is it that we want to solve, okay? If we can find a way to solve faster and better than classical algorithms a problem that actually matters, I think then we are really looking into quantum advantage. So the promises that quantum computing brings are many, okay? That it's already many years that algorithms are known that can solve some problems with a large acceleration. Problems that range from sampling to searches to optimizations, those things are things that for which we can find application in different practical application in different fields, and in particular also in physics. One thing that might be interesting here in this case is it is accepted, it is known that you can accelerate linear algebra fairly well. Okay, so this is something that could have an application in a wide range of fields. And of course, as you already saw, cryptography and communications and direct simulation of quantum systems. So those are the things that we think we could do much better now that we have access to quantum computing. There are, however, a lot of challenges related to this, okay? We cannot assume that the problems are solved and we are just going to be able to use quantum computers to fix to replace our Monte Carlo simulation, for example. And there are different kind of limitations or challenges. Some of those are related to I would say, have more of a theoretical nature. And others are instead related to the status of the hardware today. So the technology, the level of technologies we have access to. So everything that has to do with with current hardware, NISC devices. We know that it's limited in terms of the number of qubits that we can get access to, the connectivity between the qubits, the stability of the qubits. This has a direct effect on the kind of algorithms we can design and on the performance of the algorithms that we can test. There are, of course, a whole set of techniques that can be put in place in order to improve on the results. Those techniques are called error mitigation techniques, but also specific optimizations of our circuits and algorithms in order to fit the abilities, or let's say the structure of the hardware that we have at hand. And then the idea of choosing algorithms, for example, that are more suitable or more robust to the current problems, to the current limitation of the hardware. Variational approaches, for example, or anything that has to do with integrated hybrid systems between classical and quantum. This also brings me to another point. One of the questions that always arises is about how are we going to use quantum computers? How soon can we run algorithms, real algorithms on quantum computers? So probably one of the first way, one of the ways we will be able to use quantum computers the soonest is by integrating them as accelerators in larger classical infrastructure. Okay, this is something that is already happening today. You can see this with the IBM, for example. They give access to their hardware in larger, to their quantum hardware within larger classical cloud-based infrastructure, right? So this is something that we can take into account if we want to start using it for our problems today. And of course, there are, connected to this, a lot of both engineering level or kind of problems, but also, as I said before, algorithmic design. So I mentioned there are different kinds of algorithms that are known, have already been studied, have already been applied to different cases, some for many, many years already, like the Grover's algorithms or the Shor algorithms. In other cases, you can see that there are really different kind of interests in different classes of algorithms that rise over time, also depending on how the hardware evolves. Another thing that it's indirect, if you want, is a class of classical algorithm that is quantum inspired, okay? So that reproduces behavior of quantum systems, and that is actually very, very powerful. It's typically used for example, for optimization problems, okay? And that is a purely classical technique. And then there is the whole class of quantum machine learning. And you will see I will talk mostly about this today. But in general, what I wanted to stress, and this is also something that is leading really, is driving the research we're doing today about algorithms here at CERN. So if you want to apply quantum computing to solve a problem, what you need to do is to let's say, try changing the way you think about your solution. You cannot just reason in the same way you would for designing a classical algorithm. You need to start from scratch. Generally speaking, just translating a classical algorithm in the quantum domain is not going to give you the best performance. So quantum computing at CERN. So quantum computing is one of the areas that, yes?
Sorry to interrupt, but since you said that it's fine, I wanted to ask you about the previous slide when you mentioned the quantum-inspired algorithms. Could you give us like one example of one basic case where this happens?
Yeah, for example, you can, so an example in the machine learning domain is the three-tensor networks. Those were designed as classifiers that could describe the behavior of multi-body systems and quantum systems. But they can be designed as purely classical networks, basically. Yeah. So quantum computing, as I was saying, is one of the research areas within the CERN QTI. The idea is really to understand which areas, which application could profit from introducing quantum computing in it, understanding what are the challenges related to it, and also the limitations, of course. And so what we're doing in order to understand this, to study this, is to really choose representative use cases. If you look through let's say, the examples, the results that have been made public already, you will see that there are examples that cover basically all different tasks related to data processing in our experiments. Okay, this is a very broad set of applications. And what we want to do is to look at this from the perspective of near-term devices, so what we can do in the next few years with the available hardware, but also have a kind of a longer timescale view of what might be possible once we have access to fault-tolerant hardware. Quantum machine learning is among, let's say, it's a class of algorithm that has been mostly studied so far here at CERN. And there are many reasons behind that. One of those is the fact that those are general tools. If you understand how to build efficient quantum machine learning algorithms, you can apply those to very different tasks. Okay, and in general, classical machine learning is something that is becoming very popular for solving a lot of different problems. The second reason is what I mentioned before, and it's the fact that in general, those are algorithms that can behave rather well on near-term devices, okay? Now, behave and they can be robust. They have, however, a very big limitation. So there is a very big problem in using quantum machine learning on near-term devices, and it's the fact that, at least from a classical point of view, when we think about machine learning, we are thinking about analyzing a large amount of data. Okay, so right now, of course, this is kind of a contradiction. If you want to use or to analyze or to process a large amount of data, you're going to have problems on a NISQ device. What do I mean? Just to be clear, I put back this slide here just to make sure that we agree on what quantum machine learning means. It can mean many things. There are cases in which classical machine learning is actually used to improve on quantum systems. This is not what I'm talking about here in this case. What I talk about here is using quantum computing to improve or accelerate machine learning algorithms. And in order to do that, there are a few points that need to be addressed. It's not just about designing the model. It is about understanding how we can load the data set that we need to analyze on our quantum devices. There is a part that deals with reducing the dimensionality of this data to the ones, to a subset that we really need and that we can use and we can load effectively on quantum states. And then there is the part about model definitions. So I don't want to go into the details, but if you work with machine learning, classical machine learning, you know that there are some specific key features that make models perform well. One of those, for example, is the use of nonlinear activation function. Now, if you want to build a quantum computing algorithm, this is represented by a set of unitary operations. You cannot just reproduce or represent a nonlinear functions with those easily, okay? There are workarounds, but this is something that needs to be taken into account. And then the other thing, and this, if you want, is something that is common with respect to classical approaches, is the fact that what you want to do is really try to design a model that can capture, at best, the structure within your data sets. And then, of course, there is the whole discussion about optimization and convergence. So those models will live in a completely different space. The Hilbert space has a much higher dimensionality. Now, this can be an advantage because it will give you the possibility to represent over a much smaller subset of states the information, okay, with respect to what you would need in the classical world. But at the same time, it can make convergence harder. And if we look at it from that perspective, then there are different things that need to be studied. What is the best way to do optimization? How do we define? How do we map? How do we map it? So how do we connect the convergence ability of our models to the structure of the model itself? So I will just briefly go through all these steps just to give you an idea of what happens. What do you do usually if you want to build a quantum machine learning algorithm? So as far as the first step is concerned, the one that is closer to your data, how do you manipulate it before actually running your algorithms? I'm stressing here that everything you see is running on classical data. Okay, so unfortunately, as you saw before, it's not so easy to get access to quantum data, which would be great. But unfortunately, all the studies that you're seeing here are running quantum algorithms on classical data, okay? So there are different ways in which you can work on, this is, okay. It's either the battery that's going down, it doesn't matter, but I'm just saying. So there are different ways you can perform feature extraction. So as I said, you can extract relevant information while at the same reducing the dimensionality of the data you need to study. Those are typically relying on models that you can optimize by themselves independently. So, but you can also do that together with the task at the end. And for the data embedding part, so the step in which you load your classical data on quantum states, this is also extremely important. It can change entirely the performance of your algorithm, and moreover, it's really driven today. It's not driven, but let's say it's really shaped by the possibility what's available in terms of hardware. Okay, so there are different strategies that you can take, but there might be limitations if you end up building algorithms that are too big. And then we come to model definitions. There are basically two big ways of building models today, and you can think of mapping those to the two main classes of classical machine learning algorithms. The neural networks, which in this field are going to be mapped to variational algorithms, or the kernel-based methods. And you can see that there are advantages and disadvantages in the two cases. There are different, let's say, optimization that you can do. There are different also challenges that you need to face. There are different ways of adjusting their design to the data sets. Okay, but actually not a little, but there is some sort of, let's say, the way this choice is made is something that so far has been very much based on previous experience, okay? While now we are starting really to look into how to make this choice from a more, first principle kind of approach. So one example of this is really try to see, for example, how those models behave. This can have repercussion and can bring to interesting results also from the point of view, to the classical part. Okay, so the classical counterpart of all this of machine learning, right? And so there is a lot. This is just an example of the works that exist that are trying to understand how the different models behave, if they are really different, if they can be mapped into each other, and how we can leverage the advantages that come from one interpretation or the other. Now, the last thing I wanted to show you before we finish is discussion again about quantum advantage, because I think this is an important point, and it's usually the first question that is asked whenever we talk about quantum algorithms. Now, for other algorithms, it might be more straightforward. I think the case is particularly difficult to make in the case of quantum machine learning algorithms, and this is because there are different parameters that you need to look into, or that you need to be able to control when you design those. So, of course, runtime speed up is the basic definition of advantage. If you can solve the problem faster, this is, you are probably going to be happy. Now, there are other things that might be important in case of machine learning. For example, the size of the data set you need to training, or how well your neural network, your machine learning model is capable of representing of learning a meaningful representation of the data. So that is a different kind of advantage that you can look for. Now, there has been also a lot of work in trying to understand whether it even makes sense to try to do this on classical data. So it's a question that is still open. We know, for example, that one way of really getting advantage with respect to classical machine learning is to try and use the full Hilbert space that is available to a quantum algorithm. This, however, as I said before, can bring problems in terms of reaching convergence. And then, of course, there are all the aspects related to practical implementation. So you can design a very fast algorithm, but if the processing step that is needed to embed your classical data in a quantum state takes too long or is inefficient, then this might hinder entirely your conclusions about an advantage. And of course, there is the whole discussion about defining real metrics. Not real metrics, fair metrics. So how do we actually make sure that we are comparing our quantum algorithm to the best possible classical tool? Nevertheless, and I would really I'll invite you to read these publications there at the bottom, there is more that we can learn from quantum machine learning beyond just looking from, from pure advantage. There are a lot of aspects that might be interesting for even just, translating them back to the classical domain. Okay, and I close here with just a couple of slides that show you highlights of example applications in high energy physics field. I'm not going to describe all of this, it's late, and in any case, it wouldn't be the point now. There are full reference for everything. I just wanted to show you the range of applications that people are looking into. Here we are talking about B-tagging. We are talking about anomaly detection. We are talking about binary classification, so signal to background separation for different kinds of signals. We are talking about convolutional neural networks, and we are talking about a wide range of quantum machine learning models that are being tested and quantum hardware technologies that are being used. And part of this is in the same way done at CERN. So this is a collection of some of the results that are already available. The work that is ongoing is at different levels, or I would say, of readiness. But again, it really covers everything running from simulation to pattern recognition, trajectory reconstruction, reinforcement learning for beams optimization, again, event generation, and so on, and classification. And I close with this. Thanks. Questions or other questions?
Time for a question while we switch microphones.
Yes.
So, if I understood correctly, essentially you're saying that quantum advantage, or whatever we can learn from quantum technologies in machine learning, can extend far beyond simply speeding up the execution time. So right now, do we already have directions that point to answers to other open questions in machine learning, such as maybe data efficiency or foundation models?
Yeah, so there are a few examples of those. So I very briefly I didn't even entirely mention it, but so anything that has to do with understanding, for example, how to map kernel methods to neural networks, so variation algorithms to kernel methods in the quantum domain, applies also to classical. Okay, everything that has to do with understanding how you could design better your kernels by looking at the structure of your data applies there as well. The path to convergence, so the study of barren plateau, how those change when you move from a classical environment to a quantum one. All of these are, characterization of the behavior of those models that are useful beyond the specific application.
Okay.
Thank you.
Thank you, Sophia.